Thank you, Alex. Do you hear me okay? Yes? Okay.
Yes.
Okay, and you see my slides as well?
Um,
I did share screen.
Have you shared them already? No.
Yes.
I don't see them, but that could be my fault. So
Does anybody else see my slide?
Yeah, we can see the slide, but I'm not sure if
Okay.
your screen or Alex's screen. Maybe it's your screen.
Okay.
no,
Yeah.
you're seeing Leo's screen if you're seeing it. Perfect.
Okay,
Okay,
thank you
okay.
very much.
Thanks, Leo.
Thanks, Alex, for the very kind invitation and the kind words. It's an honor for me to give a talk after yours. Very impressive work, very nice work. Welcome, everybody. I'm happy to be able to share with you some thoughts about accelerating deep learning in medical image analysis in radiology. Thanks for the invitation. So this is I'm gonna present to you some an idea and some joint work with a number of people here in Israel. If you don't hear me okay, or you stop seeing my slides at any moment, please make a lot of noise so I can know that something is wrong. Thank you. So if we look at the world of clinical radiology, we clearly understand that the number of patients is increasing rapidly. We do observe a manpower shortage. Clearly, the number of radiologists grows slower than the number of patients and images. And of course, the images become more and more complex from different modalities. The treatments are becoming more complex and diverse. And this creates a great pressure on the health system, and especially on radiologists, which are in shortage and therefore required to do more and more work. Never mention, of course, the issue of the COVID, which has even strained even further the work that our colleagues, the radiologists and different clinicians have to do. On the other hand, if we look at the technical factors, we now live in a connected world with a high bandwidth and the ability to transfer data easily and have this wonderful teleconference, which was unthinkable several years ago. And of course, the computer and networking power has increased very significantly. And the focus of my talk is, of course, what you're familiar with is the new AI technologies. But the bottom line is that really what you're looking for is to optimize the automation and workflow, because this is what happens when you have great pressure in a certain industry. If we take two parameters, the radiologist time, it can be a radiologist or a clinician, of course, and let's say accuracy in any way you would like to measure it, okay? And of course, you don't always need 100% accuracy. You need sufficient accuracy so that you oversee the clinical requirement. So for example, if you're doing a follow-up of tumors, you only need to be precise to a certain degree. And what we observe is that in the current practice, most of the assessment is still done manually. In other words, even if there are computer tools to visualize the images, to zoom in and do different things, most of the quantitative assessment and qualitative as well is manual, and it is not clear what is that clinical requirement. So different subspecialties and different diseases have different values for what this clinical requirement is. And we observe that in many cases, because of the shortage of radiologists' time, if a radiologist has to read 20, 30, or even more scans per day, obviously there's going to be a time pressure. And in some cases, the current practice is going to be below what this clinical requirement is. The goal for the paradigm shift, what we're looking for in this new practice is basically with the help of computer support to move this graph to the left, meaning you reduce the time and increase the accuracy in such a way that you exceed the clinical requirement. And you can also quantify that. And then you have really help doing something about the workflow. Note that the goal is not full automation, but rather to engage the clinician in a way that you can provide effective information. So we're looking for less time, we're looking for higher accuracy, and a third parameter which is very important is the observer variability, because there is no such thing as an absolute ground truth. And this is also, of course, patient-specific and scan-specific. So there is a margin that contains this clinical requirement, which is the observer variability. And we observe that in the manual case, this is quite wide. So if you see the band around the variability for the manual assessment, we know that it can be quite large. And the goal with our computer support would be to also both quantify the observer variability, but also to reduce it. Okay, so in other words, you might have uncertainty, but you can quantify what is the level of uncertainty, and this has to be patient specific and of course span specific. If you achieve and manage to lower this variability, you have really achieved the three objectives that would eventually lead to a better treatment. So just to emphasize a point, the goal is not necessarily to automate everything. The goal is mostly to be more effective and reduce the engagement of the radiologist, so they engage the radiologist in a smarter way. Okay? And nowadays, this has been done in the field of medical imaging and radiology with deep learning methods. And this has become the method of choice. And in fact, there is a lot of buzz about it, not only in our technical community, but also in the radiology community. You see venues like the RSNA or the European Radiology Conference, different companies really are very excited about this technology. It even, as all the hype goes up, goes to the point in which they say, is the future of radiology doomed? We very well understand that this is not the case. We don't believe that AI will replace the radiologist anytime soon. However, I've heard that it will replace radiologists that do not use AI. And the idea is to create the tools that radiologists can do a better work. Okay. So the problem with deep learning is, of course, data annotation. You need lots of them, at least what we need nowadays. And this is, if you wish, the fuel of this technology. We have a great car, a Ferrari, but now it's very expensive in terms of fuel. So what are the main issues with these annotations? Because with no annotations or with poor annotations, you cannot do any kind of reasonable deep learning. So of course, the annotator expertise is an issue. Highly trained radiologists do not want to spend their time annotating images, even if they're paid. I mean, this is not reasonable. So we have to establish some sort of a time budget. The time, of course, also determines the price because the radiologists are going to have to be paid. And of course, in this case, we need to optimize that. We need to understand what is the annotation quality. And of course, because deep learning is based on a sample of an unknown distribution of cases, you need sufficient examples to be able to train a deep network to be able to cover and achieve some sort of robustness. The case distribution is key, and you need to explore that in an incremental way. And of course, the observer variability, which I mentioned, the goal is basically to build a system that is within the observer variability, and we need ways to quantify this observer variability because they change from case to case. So a brief illustration of the observer variability, what we aim for. This is a CT of a lung, and this is a lung tumor. It's upside down for ease of viewing. And we asked 10 radiologists at the radiology department here in the hospital in Jerusalem to annotate this. And this is what you get. Each color shows the annotation of one of these radiologists. And you see that there are areas of very high variability, and this is natural. Why is it natural? Simply because you don't see a clear boundary there. You can see that even the number of components can change. So we understand that the manual segmentation variability on which we're going to base our deep learning models or annotations can have a very wide variability, and we need to understand and quantify that. And this varies very much. It's not only the number, but the range. You see that the range is from 5 to up to 50%, which is very significant in building different models. And it changes by structure, case, and observer, and we published several papers on the case. The good news, though, is that this variability can be quantified and estimated. Okay, so the fact that it's there, you have to embrace the fact that you have the observer variability, and there are different ways to estimate that. But this is, of course, the subject of a different talk. What I want to focus today is on the bottlenecks. So we have this great technology and we're developing AI-based radiology solutions. What would it require? We know that it does require a large collection of representative data sets. If we're doing segmentation, the two key tasks of the analysis, the technical task would be segmentation and classification. If we're doing segmentations of structures, we need around 1,000 to 5,000 annotations to achieve really robustness and coverage. And if we're doing a classification, a binary classification or classification into a small number of categories, such as healthy, non-healthy, or moderate, severe, and so on, you need about 10 to 50,000 annotations. And obviously, this is going to become very expensive because the manual expert annotations, this would require about 1,000 hours of a radiologist or several radiologists for the initial deployment of the network. And then because you're sampling this unknown distribution, you're going to need a similar amount for robustness and coverage. Those are very, very rough estimates, which vary very much from case to case. And in addition, you're going to have to do this custom development for hundreds of specific organs, structures, and pathologies, and also imaging protocols, because what we know already is that these networks are very sensitive to the different resolutions, imaging protocols, and so on. So if you think of a RAD app, an application for radiology for each one of these pathologies or characteristics or the clinical question that you're asking, you're basically going to have to develop one of those from scratch for each one. And this is what is called a narrow AI. And this leads to a lengthy and costly development process. You know that eventually it's going to work. If you have sufficient annotations, you're going to be able to train a network to do the proper job. But this is going to be a lengthy and costly development process. And if you think a little bit wider, this is what narrow AI does. It takes a long time and it incurs in a very high cost. So if you see this matrix in which you see different pathologies, different areas, of the body, different imaging modalities, and then you can think of the third dimension. You can have the different pathologies. There are hundreds of those. This is a huge matrix, and every RAD app that you're going to develop is going to target one of these entries in this matrix. So this is going to take a very long time. And it's in fact not going to be cost effective for the vast majority of the common conditions. The low-hanging fruits are being picked by research labs and different companies, which do have the budget to develop that. We're talking about several million euros or dollars for each one of these slots. So obviously there are some conditions which it's not going to be cost effective to develop such solutions. Okay. Of course, there are tools that try to address these, such as transfer learning, one-shot image classification, but still this is in its infancy, I would say. So we are faced with this task that to fill this matrix, we basically need to invest a lot of effort and time, and not necessarily us as technical people, but mostly our clinical partners because of the annotations. Okay. So what we see now is that we need to involve the radiologist in this loop. Okay, and this is called the bootstrapping radiologist. You would have to start by collecting and annotating a few scans, because without that, there is no way to build a network. Then you develop and improve the model, you deploy it, you validate and correct. It's not fully automatic, but it has to be sufficiently worthwhile so that you provide useful results earlier. You optimize the radiologist time and budget. It's not the tedious delineation from scratch every single time. And you have to do the software improvement or the network training on the go. Okay. Otherwise, you are not going to be able to make progress, and you have to accommodate rare cases that can be handled in a semi-automatic or fully manual way, but you have to identify those. Without this, all these RAD apps are going to basically remain in the lab. So let's look at the different qualities of the radiologist validated annotations. Okay, and I view this as a pyramid because you're going to have high quality annotations at the top of the pyramid, very few, and low quality annotations, those have not been validated, at the bottom of the pyramid. Okay, so here you would see is the following. You have in this horizontal axis the quantity, and you have the quality of the annotation of these data sets. And of course, with quality, the cost increases. What is the top of the pyramid? You have two independent experts that have manually annotated the data set and reached the consensus. So this is the highest quality of annotation. On the other hand, the lowest quality is those that are automatically generated, that have not been corrected or inspected by an expert radiologist. So you're not very sure about the quality of these. And these you can generate many because you can basically run your deep network on any scan that comes in and get some results. So of course, there's gradings in this pyramid. If you have a single expert, that's the next best. Or if your network generates a segmentation, for example, and it's corrected by two independent experts, that's the next quality, and so on. You can, of course, involve graduate students and different types of expertise. And this way, you're going to get a hybrid set of annotations with which you're going to train your network. So you're going to start with a low or mixed quality of annotations, the minimum required to train the deep network. And then you're basically going to add to that. But of course, this is going to be a very expensive process because the quality of the improvement is uneven. You don't really have a quality control. You don't have a measure for observer variability, and you don't really have an indication of what is missing. Basically, you're expecting data to come in and see what happens. What we're looking at is to involve the radiologist to validate and correct a subset of these, such that with the same annotations that you have, you basically move them up the pyramid to obtain high quality annotations. Because we know that empirically, a network trained with high quality annotations performs much better than one and requires less annotations than one that's trained with less data. Then you train your network, and the goal is to optimize the quality, to reduce the number of data sets, and to identify and add rare cases. So if you wish, in mathematical terms, you're basically looking to optimize in this pyramid. CI is the cost of each radiologist. There are different types of radiologists and expert annotators, and TI is the time. You're basically looking to minimize this time to improve the quality. So this is what we're based at. Large companies might be able to do this in a large scale for a number of selected conditions. But what about those of us who don't have access to this type of annotations, for example, in the different labs? So in my lab here in Jerusalem, we have been doing applying a systematic methodology to optimize with the radiologist in the loop the different the annotation time. And I'm going to show you today the first one, which is fetal development MRI. And the goal here is to basically describe to you very briefly how you can optimize this annotation, how you involve the radiologist and get what you need. So the task we're looking at is a fetal MRI development evaluation. A pregnant woman goes through an MRI, and from this MRI, you can get information which is not available in traditional ultrasound, such as the fetus, an accurate measure of the fetus volume, the fetus brain, and different morphology of the fetus brain, and also the placenta, which feeds into that. And in addition, you want to produce linear measurements, which you can compare with ultrasound-based measurements. And you'd like to be able to do all this automatically, of course, with the minimum number of training annotations. Okay. The clinical significance of this work is that you can then generate a quantitative report with measures of variability and uncertainty, and basically determine from the fetal development curves what the conditions are available. So I'm going to focus, of course, only on the aspect of how do you accelerate this pipeline. Okay. So in the initial phase, there's no other choice but obtain those manual segmentations for each structure. Should mention that for these structures, it takes over an hour for an experienced radiologist to annotate these MRI data sets. We train a deep network for these type of structures, make corrections with another network, which I will show, and then basically generate a higher number of annotations, about 50 to 100 in this intermediate phase. You train the network, and then based on the corrections that the radiologist has done, you can do a segmentation error estimation and also segmentation error correction automatically. And most importantly, you can prioritize. If you run the next batch of 100 MRI scans, you can say which ones are worth looking at, which ones should be corrected by the radiologist to avoid going through every single slice and every single scan. So here's the basic idea of the interactive learning from user corrections. You have this network that produces trained with very few scans, in this case, 8 or 10 scans, which is about 800 slices. You train the network, and now you're going to ask, this would be the result. For example, this is the fetal body. You train this, and then you're able to correct. You ask the clinician to correct this segmentation, the manual corrections in a certain slice, and then you propagate, you learn what these corrections are and propagate it to the next slide. So you can see that slice n+1, there's still some errors, but you see that some of the segmentation errors that you see here, for example, in the bottom of the slice, have disappeared because the specific network has learned how the correction should be made. Okay, so the idea then is that if you take the time that's required to produce this validated segmentation, fully manual segmentation takes about over an hour, as I said. This is the volume overlap difference. At the beginning, you have 100% difference, no segmentation. As the time goes, you reduce to the observer variability. If you train the network, you would have to correct about 35% of the segmentation, and doing that manually, as you can see, doesn't buy you much. In other words, even if it's less work, presumably, it doesn't take less time. There are too many corrections to do, so it's not useful. However, if we use the approach that I just described, you can create these corrections and reduce the time very significantly to about 8 minutes, and the end result is a validated high-quality segmentation. Okay, because of this propagation scheme, you need to correct on average 1 in 5 slices, and it takes also less time, and you reach the same observer variability than the full manual. So once you have this initial phase, you train again the network. Now you have these high quality annotations, and it's going to do relatively well on similar scans. However, the challenge here is going to be the scanning protocol, changes on that, the gestation age in case of the fetus, and where the scan was acquired. Okay, so you can acquire those scans and run it, and you're going to get hundreds of segmentations, but who's going to look at them? All these required validation. There are too many slices to inspect every one. So what you want to do is to do an estimation of the segmentation uncertainty, do a prioritization of which scans can you correct, and then ask to correct only those. So just to quickly illustrate the process, you compute the segmentation uncertainty like here. Some of it is uncertainty and some of it is error. And of course, you don't know this ahead of time. You can see in this, the blue margins show you the uncertainty of the network. And here, some of it is an error, some of it is uncertainty. It's a valid uncertainty. And with methods that I would not describe, basically, you can learn what this segmentation uncertainty is based on the manual corrections, and basically, in some cases, correct some of that. In this case, for example, with a network that has learned how to do the corrections, this disappears. Okay, and this is the network that inputs this automatic segmentation error correction. You input the corrected segmentation and then correct that in the subsequent slice. And based on this, you can prioritize the scans in decreasing order of uncertainty and then ask the radiologist to test that. So just to briefly give you an idea before I finalize is the following. We tested this on 3 structures from fetal MRI scans: the fetal body, fetal brain, and the placenta. You see here the numbers with different protocols. How we started the initial phase with 13 scans for the body, 12 scans for the brain, and 10 scans for the placenta, and then basically reach this intermediate result. Okay, and the focus was, if you look at the dice coefficient, we know what is the slice correction prioritization. This is the initial for error, the 1 minus the dice coefficient. And as the number of slices, the percentage of slices is corrected from 0 to 100% of the slices, you can have the optimal one, which is if you know ahead of time what the correction is, this is the order. But if you do it sequentially, you get a certain number. And if you do it with uncertainty, you reach this. So what we can see is that if you do it a slice-wise, you only inspect the number of slices. After 12% of the corrections, you can already reach the observer variability of 9% in these cases, versus 33% of the slices when you do this sequentially. So basically, you have, in this case, in this study, the inspection and correction of about 12% of the slices achieves the observer variability performance instead of 33%. So the gain is very significant. This is what the dice per slice would look like. You have here the dice coefficient and the slice number. At the beginning, this is the original correction, the manual correction with no propagation. This is what the dice coefficient does. In some cases, it usually goes up, but not always. If you do the prioritization, as you can see here, you reach the same dice coefficient with less slices. Okay, so you save on average about 60% of the manual corrections. Okay, another aspect is which scans can you add, and in this case, we can add 5 scans. And here we again did a study in which, based on the uncertainty estimation, we can choose, after you have segmented 100 scans, which ones are the 5 ones that are worth correcting and adding. Okay, so just to summarize, the current status of our work is that we created 322 high quality segmentations. By high quality, we mean that they have been validated by a radiologist with a modest effort and the same team. Here are the numbers. We are able to cover different protocols and different sequences of different resolutions. And we're able to do this based on this scheme. And we're now processing an additional 300 for the development of these curves. Okay, and this is the work in progress. We do a similar approach for the linear measurements. I will skip the details, but the idea here is that we produce, without doing the segmentation, these linear measurements, and we want to do that with as few as possible of the measurements. We do this with about 200 linear measurements of manual annotation that include both the slide selection for the measurement and the actual measurement itself. Okay, so you see that with 214 scans, the annotation of 214 scans, we were able to reach the observer variability as desired. Okay? So to summarize, what we can say is that this approach that I have just described to you allows us to reach the observer variability and do a bootstrapping of this methodology on as few as possible scans. The prototype is in use at the Tel Aviv Sourasky Medical Center for the research on 3D fetal development. Okay, and this could not been possible without the radiologist in the loop and this bootstrapping technology. So to conclude, unless we develop approaches similar to the ones that I described to you, we're not able to achieve the narrow intelligence that we're looking by deep learning for specific tasks. Because in the end, the bottom line is the expensive and time-consuming effort of clinicians, which are not annotators. The low-hanging fruits, as I described, are being picked by companies and different research labs. But I believe that in the next 3 years or so, all of those will be picked and the rest is going to be the next level, those who are less cost effective. And for this, we need to develop the technologies that we're talking about. And the clinician in the loop is a key component for the bootstrapping here. The long-term viability of deep learning then presents very significant challenges, mostly because of the annotation effort. Just a brief thank you to all the colleagues and collaborators from the different institutions and students. And this is what our lab meetings look like. The good news is that we've coming back to meetings in person. The first one is going to be held next week because we already have a high number of vaccinations here in Israel. All the students have been vaccinated and we're going to resume the in-person meetings and we're very excited about that. Thank you for your attention. As Alex mentioned, I'll be happy to answer questions by email or any other means. Thank you very much.
Thank you, Leo. It was a fantastic talk. And I think your main point is well taken, that probably is not only about developing new networks, but also developing new schemes on how to train them more efficiently and get humans in the loops. And that's quite interesting. One thing I'd appreciate if you could answer in the chat
Sure.
is if you have any experience about how the results you show would change with the type of network, because you use the same network most of the times, right? It's CNN. So whether is there any point in improving networks or not, or is it actually most of the impact coming by the sort of training and schemes that you mentioned? And I would be curious to know if there is any publications that you are familiar with or you've done on that space.
Thank you. That's an excellent question, Alex. In fact, what we've observed is that there are different phases. Changing the network might be useful at the very beginning. There are networks that require more training examples and networks that require fewer network examples. But as you move and your dice coefficient and accuracy moves up, then the architecture doesn't matter anymore. You have to focus on the loss function and other parameters. So because we're doing this with about 10 different structures and types of scans, we're beginning to understand when it's worth applying what networks to what efforts. We, for example, know that when you already reached the observer variability, changing the network architecture is not going to buy you much. However, in different steps of the development, it is worth doing. So basically, we're developing the methodology, and still no paper, but hopefully soon, that describes these phases and what is worth doing at every step, backed, of course, with empirical data, because this is mostly empirical science.